Welcome. In this session, we will continue our discussion of implicit differentiation. Often, we are interested not in the derivative of an implicit function in general, but the derivative at a particular point. Then, rather than to find the implicit derivative in general and then substituting the coordinates, we can first substitute the coordinates, then solve for the derivative at that point. To illustrate what I just said, we'll do an example. This is one of the economics concepts I've seen before, the marginal propensity to consume or to save. Difference this time is that we have an equation connecting income and savings rather than the savings given purely as a function, an expression in income. So I have the equation s squared plus 0.25 I squared equals I plus IS, where S is the savings, I is the income given in billions of dollars. And I'm trying to compute the marginal propensity to consume given the income and the savings. So again, we can solve for savings using the quadratic formula, but it's a lot simpler to use implicit differentiation rather than to try to differentiate the expression we get from the quadratic formula. So I'm going to differentiate both sides of the given equation, but treating S as a function of the income I. So on the left hand side, the first term is S squared. So it's a function squared. By the power rule, I first differentiate for the exponent 2, which gives me 2s, and then I differentiate the inside s. Since I don't know what it is, I leave it as ds over di. The second term has only I in it, so I differentiate as usual. Derivative of I squared is 2i. 0.25 times 2 is 0.5. On the right hand side, the first term is derivative of I with respect to itself, which is 1. The second term I have a product, so I have to use the product rule. The first factor is I, its derivative with respect to I is 1, times second factor s, plus I times derivative of the second factor. Derivative of the second factor is derivative of s, so we just use the placeholder ds over di. Now I can solve this for ds over di first and then substitute 16 for I and 12 for s. Or I can do the two things in reverse order. I can substitute 16 for I and 12 for s, and ds over di is really the value of the derivative at that particular point. I'm not going to reflect that in the notation. Otherwise it looks rather messy. The advantage of doing this is that we have a numerical equation to solve. The only unknown in this equation is ds over di. Everything else is a number. So we're going to simplify. So do the multiplications. 2 times 12 is 24, 0.5 times 16 is 8. And then collect ds over di terms on one side. I'm going to move the 16 ds over di to the left. So subtract 16 ds over di, which on the left gives me 8 ds over di. And then subtract 8 from both sides, which gives me 13 minus 8 or 5 on the right. So ds over di at the point I equals 16, s equals 12 is 5 over 8. And the marginal propensity to consume is 1 minus the marginal propensity to save. So that's 1 minus 5 over 8, which is 3 over 8. Now if I had done it the other way, if I had solved this equation for ds over di, I will leave the algebra to you. You just bring the ds over di to the left and then move the 0.5i to the right, and then divide by the coefficient of ds over di after factoring that out of the left first. Then you get 1 plus s minus 0.5i divided by 2s minus I. And if you substitute 16 for I and 12 for s, you get the same answer, 5/8 for ds over di. This really goes back to algebra. In algebra, simplifying and then evaluating is equivalent to evaluating and then simplifying. So if I have to find the implicit derivative at a particular point, I will generally use this approach. Substitute the coordinates of the point first and solve the resulting numerical equation. We will use the same technique to find equation of a tangent to a curve with a given equation when we have to use the implicit derivative. We will do an example of this next time.